In this video, I'll be talking about inverse functions. So first of all, let's talk about the basic idea. Inverse functions undo one another. So that's the basic idea. Think of the word opposite, kind of like inverse. So basically, inverse functions do the opposite thing. Excuse me. So let's look at f of x equals 2x here. Notice this function doubles each input. So if you plug in a number, you're going to multiply it by 2. You're going to double your value. So f of 1 would be 2 times 1, which is 2. F of 2 would be 2 times 2, which is 4. And f of 3 would be 2 times 3, which is 6. Now notice my inputs are 1, 2, and 3 here, and my outputs are 2, 4, and 6. Now let's go ahead and write down some of the points on the graph of f. We learned that if f of 1 is 2, then that tells us there's a point on the graph, the point 1, 2. And if f of 2 is 4, then 2, 4 is on the graph. And if f of 3 is 6, then 3, 6 is on the graph. So basically, we have an input and an output with the points here. Basically, f of 2 equaling 4 gives us the same information as this point. Excuse me. I'm sorry, I'm losing my voice here. All right, so if I said, what would be the inverse of this function, what would it be? What function does the opposite of doubling an input? Well, of course, that would be taking half of an input, or x over 2. G of x equals x over 2. So this function halves each input. So let's go ahead and plug some values in here. So remember, we had f of 1 equals 2 on the left. Let's kind of reverse that, and we'll say, what's g of 2? Well, you'd get 2 over 2, which is 1. And we said f of 2 was 4. What if we plug the 4 into g? Then we'd have 4 over 2, and we'd get 2. And if we said f of 3 was 6, in the inverse function g of 6 gives us 6 over 2, which reduces to 3. So hopefully you can see what's going on here. So there's a nice pattern here. Notice the points on the graph of g. That would be 2, 1, 4, 2, and 6, 3. So these are the same exact points that we got for f. They're just in reverse order. And so we've got a pattern here, or discovered a pattern. Notice that if AB is a point on the graph of f, then the point BA will be on the graph of G. There's going to be several of these, what I call inverse facts, that we'll establish along the way in this lesson here. The second thing I want to mention, excuse me, is f and g are inverses of each other. I could have started with g, and the inverse would have been f. And then finally, there's a notation that we use for inverses. The inverse of f is f inverse. So that's how we write the inverse. We read that f inverse. Now be careful here that -1 has nothing to do with exponents. It's just a notation for the inverse of f, or what we call f inverse. So notice f inverse does not equal 1 over f of x. Just like if you had 5 to the -2, that would be 1 over 5 squared. That's not what we have going on here. So this is not an exponent, it's just a notation to represent the inverse. All right, let's move on to the next slide. So it says here, for each set of ordered pairs, or each relation, determine whether the relation is a function. If it is a function, find its inverse and determine whether the inverse is a function. Now, if you remember what we learned about functions, particularly ordered pairs, or what makes a function when you're looking at ordered pairs, you might try to go ahead and follow directions here and then watch the video. All right, so we previously learned that a set of ordered pairs is a function if x doesn't repeat. So notice for f, the x values don't repeat. That's going to be a function. The other way to describe a function, and this is a description I gave you before, one that I would want you to remember, and that is each input has exactly one output. That's what's always going to be true with a function. So we said f was a function because the x values don't repeat. But the other way to look at it is if you look at each input, they have exactly one corresponding output. 1 corresponds to 2 and only 2. 2 corresponds to 3 and only 3. And 3 corresponds to 4 and only 4. Each of my inputs corresponds to exactly one output. Now to find the inverse, all we have to do is flip our x and y values. All right, what about g? Well, notice, I'm sorry, I forgot to say f inverse was a function. Let's go on to g. So notice these 2 points have the same x value, and in fact f of 2 is 3 and f of 2 is 5. So it's not true that each input here has exactly one output. 2 is an input that has 2 different outputs. And so this is not a function. So again, you can look at it either way, but it's not a function. And then if you look at h, certainly h is a function. The x values don't repeat. Let's go ahead and find the inverse. We're just going to flip our x's and y's. And notice this is not a function, and that's mainly because of these 2 points here. Notice x repeats. So we'll come back to h in a couple minutes. I want to mention another thing here. If I asked you to find the domain and range for f and f inverse, we would just, let's go ahead and do it for f first. The domain is going to consist of all the x values. The range will consist of all the y values. Now, if you look at the inverse function, the domain is going to be 2, 3, and 4, and the range is going to be 1, 2, and 3. So notice what we have here. The domain and range are opposite here. So the way I like to say it is kind of basic. For any function f and its inverse f inverse, the domain and range are flipped. They're the opposite. And it really goes back to this idea of flipping our ordered pairs or flipping our points. We're doing that with every point on the function, and so our domain and range will also be flipped. All right, so we're going to talk about one-to-one functions next. It says a one-to-one function is a function such that each value of y corresponds to exactly one value of x. Another way to say this is that y doesn't repeat. So notice h is not one-to-one. The other way to say it is different inputs have different outputs. So certainly on h, you can see that the y values do repeat, and the problem is when you switch your x's and y's, now your x's are going to repeat. Another way to point out that it's not a one-to-one function, notice here it says different inputs have different outputs. Well, that's not true for h. Notice h of 2 is equal to 3, and h of 4 is equal to 3. So here you have different inputs, and we don't have different outputs. And so this is another way to see that h is not a one-to-one function. It says which function in example 1 is 1-to-1, and that would be the first one. Each of our inputs have different inputs, they're all different, have different outputs. So basically x doesn't repeat and y doesn't repeat. So f is the only one that's like that. Now next here it says, note to be a function, the x values cannot repeat. Graphically, this means it passes the vertical line test. Well, what about one-to-one functions? Well, I want you to consider the function h. That's this one here. I'm going to go ahead and graph these points. And so look at what we have here. Now remember, the 2, 3, and 4, 3 were the problem because the 3 repeated. And notice what's happening on the graph. Those points lie on a horizontal line. So the way to test for a one-to-one function is to take what's called the horizontal line test, or to use the horizontal line test. So if a function or if a graph does not pass the horizontal line test, then it's not a one-to-one function. Now notice this right here. It says every function has an inverse, and really this is what I want you to get out of the discussion we just had. Every function has an inverse. However, only one-to-one functions have inverses that are also functions. And when we're doing algebra, we normally care about functions. We don't work with things that are not functions for the most part. Let's go ahead and move on to the next slide. So determine whether each function is one-to-one. So if you look at A, notice there are several places where this one does not pass the horizontal line test, and so this one's not one-to-one. Again, let's discuss why. Notice those 2 points. Let's see, we have -1, 1 and 1, 1. Notice the y value repeats. And again, different x values don't have different input or different inputs don't have different outputs. So in any case, that's not going to be one-to-one. Notice B is okay. No matter where I draw a horizontal line, I can only go through one point. So that one is one-to-one. And the same thing is true with C. That's also one-to-one. All right, on number 3, it says graphing inverse functions and finding inverses. It says graph the inverse of f. Well, we've got 3 points that it shows us here, some nice values, and then a curve. So why don't we go ahead and write down some of those points, or actually all 3 of those points. We've got -5, 1, -2, 2, that's this one here, and also -1, 4, which would be that one there. So if those are points on the graph of f, then we know for the inverse, all we have to do is flip the points. And so let's do that. We're going to get 1, -5, 2, -2, and 4, -1. Notice all we're doing is switching the x and y values. We don't change any signs. We're just switching the x and the y values. So now let's go ahead and plot those on the graph, and we can draw the curve. And hopefully you can see that we have some symmetry here. In fact, it turns out that you're always going to have symmetry through this line here. Do you remember what that line is? That's y equals x. That was one of our basic functions. And so we have this general rule: the graphs of a function and its inverse are symmetric with respect to the line y equals x. Now on the domain here, remember with the domain we go from the leftmost to the rightmost point and we look at x values. So here we're at -5 and here we're at -1. And so our domain is going to go from -5 to 1. Now for the range, we're going to go from the lowest point to the highest point, and they're actually the same points. And so at our lowest point, we're at 1. Whoops. And our highest point, we're at 4. And so our range will go from 1 to 4. So notice what this is saying. When it says the domain is -5 to -1, that means our x values, if you look at all these points on the graph, the x values go from -5 to -1, and we're hitting everything in between. Similarly, if you go from the lowest point to the highest point, the y values are going to go from 1 to 4. All right, so if you find the domain, you'll see for the inverse, you get 1, 4, and the range is -5, -1. And really, as long as you did the domain and range correct for f, all we have to do is switch these out, just flip them or switch them, and we've got the domain and range for the inverse. All right, on B, it says graph y equals 3x minus 2 and its inverse. Well, this is a line in slope-intercept form. So when we graph these, we start with the y-intercept, which is 0, -2, and then we apply the slope to get to another point on the line. All right, so and since we're applying the slope, we want to write that as 3 over 1. Remember, it's rise over run. So we're going to start at 0, -2. And we're going to go up 3 and right 1. That puts us there. And then we can do it again, up 3 and right 1, and we end up there. I'm just getting an extra point here. Now, you don't really have to do the little part that I did in green there, but you should graph the line. It looks like that. Actually, I'm going to go ahead and erase the green here. Whoops. Wrong one. All right, and then notice we've got 3 points on this line, so why don't, and by the way, that's the line y equals 3x minus 2. So 0, -2, 1, 1, and 2, 4 are the points that I've used to draw the line. So to find the inverse, all we need to do is switch our x's and y's, and we'll get -2, 0, 1, 1, and 4, 2. Now we don't even know what the inverse is called at this point, but we can use these points to graph it. So let's go ahead and do that. And again, notice you're going to have symmetry through the line y equals x, which is always going to be the case. And let's see, I think we're ready to move on. By the way, if you found the domain and range of the original function y equals 3x minus 2, you should recall that a linear equation has a domain and range of all real numbers, except for the special cases. And if you flip the domain and range, you're going to get all real numbers for the domain and range of the inverse. All right, let's go ahead and move on. So on number 4 here, it says write an equation for the inverse of each relation. Now a relation actually represents a set of ordered pairs. It may or may not be a function. We know for A that we're dealing with a one-to-one function. If you graph that line, it does pass the vertical line test, or the horizontal line test, and the vertical line test. But really all we need to do to write an equation for the inverse is just switch our x's and our y's. Just like we did with our sets of ordered pairs, we flipped our x's and y's. Same idea here. And so you should be able to go ahead and do B. So all we have to do is switch our x and y. I'm going to go ahead and put the x squared and then the y. And so that's all there is to a problem like that. Now it's time to actually find an inverse given a function. And there's 4 steps that we use. So I'm going to go ahead and use the 4 steps as we do this problem. We'll start with number 5 here. So step 1 is to replace f of x with y. Oh, I'm sorry. It does say determine whether the function is 1 to 1. Well, we actually graphed that just a minute ago, and you can see that it does pass the, remember we have this guideline, a function is 1 to 1 if its graph passes the horizontal line test. And the one that we just graphed up above is definitely 1 to 1. All right, so now we're going to go ahead and find a formula. We didn't actually have a formula for the inverse up above, but now we're going to have one. So now we'll go ahead and replace f of x with y. So we get y equals 3x minus 2. And then it says in step 2, switch x and y. So that's one of our key steps. That's that basic idea of flipping our points. Here we're switching our x's and y's. Step 3, which is the other key step, is to solve for y. So I need to get rid of the minus 2 there. I'll add 2 to both sides. So we're going to get x plus 2 is equal to 3y. Again, I'm trying to solve for y, so I need to get rid of that 3. Let's divide by 3. And so we're going to get y is equal to x plus 2 all over 3. Now you could write that as 1/3 x plus 2/3, but there's really no reason to do that. Don't forget your last step. We're just going to replace y with f inverse of x. So I want you to notice steps 1 and 4 are really just about notation. We changed to the y notation because it's easier to manipulate an equation when it's in that form. But then when we get to the end, we want to switch back to the function notation. But at the end, you're writing it using the inverse notation. So the key steps really are steps 2 and 3. I would encourage you to try number 6 and then watch the video. Well, remember, we are supposed to determine whether this function is 1 to 1. And this is a function we know pretty well. This is the graph of y equals x cubed, vertically moved up 4, or shifted up 4. It's also what I call the John Travolta. So you can see that this does pass the horizontal line test, so this is 1 to 1. So now you should have replaced g of x with y, and then we need to switch our x's and y's. Step 3, we need to solve for y. So first of all, I need to get rid of that 4. We'll subtract 4 on each side. We get x minus 4 equals y cubed. Now I need to get y by itself. I got to get rid of the cube there. I'm going to go ahead and switch sides here. Doesn't matter which side we put the y cubed on. Since I'm trying to solve for y, I want it on the left. So now I need to think, what do I need to do, or what's the opposite of cubing? Well, that would be taking a cube root. So if I take the cube root of both sides, I'm going to get y on the left, and on the right, it's just going to be the cube root of x minus 4. And then don't forget your last step. You're going to get g inverse of x is equal to the cube root of x minus 4. All right, I'm going to go ahead and stop this video here, and I'll finish up in another video.